Hello, my name is Nathan Farmer, and welcome to my presentation on our second lab, Lines of Charge. The purpose of this lab was to compare calculations of electrical force between two charged pieces of tape when we're modeling it as a system of either two point charges or two lines of point charges. The reason for this being two lines of point charges is likely going to resemble the real world data more accurately, as we know that there are lots of different charged particles interacting between the tape, and it's going to be closer to that reality. So some principles during this lab that we had to keep in mind were Coulomb's law and electric fields, obviously, because we're going to have to calculate those electric fields and electrical force in order to compare them between the two models. And then also here, superposition is going to be very important because we're going to be summating lots of different charge particle interactions rather than just having the one interaction. Also, Newton's second law here is going to be very helpful because we're going to have to calculate that gravitational force on that top tape and using that as a reference for our net electrical force. So the experimentation for this lab was essentially the same as the second half of the last lab. We just created two equally sized pieces of tape and then calculated the mass of both of those pieces of tape, charged them by placing them on top of another piece of tape on our desk and ripping them off, and then suspending one of those pieces of tape so that had a little bit of slack in it, and then as you can see in this diagram, taking another piece of tape and trying to get that top piece of tape to float motionlessly. So once we could successfully do that, we want to measure the distance between the two pieces of tape and take the mass and that distance to use that to calculate that charge on them if we just represented it as a point charge. That was in the first lab, and by taking that information, which in this case happened to be 1.04 times 10 to the negative 8th coulombs, and taking the mass and the distance that we had, we can now calculate, by using a new program, calculate that model as two lines of point charges and then compare the two. So like I just said, we take those stored values of mass and the charge and the distance, and we plug them into this new function, and also we take my function for calculating E field from the last lab and we put it into this new function. And essentially what this program does is I specify how many point charges that I want on each line of tape, and then it'll create a list that long detailing the position and charge of each individual point charge on each line. And I can take that information and pass it into a final function that's going to go through each of those charges on the top tape and calculate the electrical field and force at each point, summate them, and finally I can represent that net electrical force and calculate the gravitational force and represent both of those with two arrows from the pieces of tape. So some assumptions that we had to make here were that the charges on both pieces of tape are going to be equal, and it's going to be evenly distributed across the strips. Obviously this isn't going to be true, but this is just an assumption that we're going to have to make here. And then also the tape can be represented as a single line of charged particles rather than a sheet of them, whereas the sheet is likely going to more accurately represent a piece of tape, but a line is more accurately going to represent a piece of tape than a singular charged particle. So originally my calculated charge for this tape was 1.04 times 10 to the negative 8th. When I pass this into the function, as you can see on the left here, the electrical force created, you can see as a white arrow, was very small and much less than the yellow arrow. So what I had to do was I had to play with that value, that charge, and eventually I got it to 2.246 times 10 to the negative 8th, and that was the value that got the gravitational force to equal out to that electrical force. And honestly, the second value, 2.246 times 10 to the negative 8th, is likely going to be much closer to the actual value in real life of the charged pieces of tape, because this model much more accurately describes the real world situation. Like there are many charged particles that are interacting between these two pieces of tape, and to just calculate it as a singular point charge isn't really going to give you a very accurate answer. So using these two lines of charges, it's likely going to be much more accurate than that original value we calculated last lab. All right, thank you very much.